Hey everyone, we are going to talk about the Pythagorean theorem today. Some of you may have learned this before and some of you may not have, but we will go through all of the details that you're going to need to know about this theorem. So first of all, the Pythagorean theorem is a relationship that only applies to right triangles. Okay, so let's go ahead and draw a right triangle in here, and obviously it's going to have a right angle. And when you look at the three side lengths, you can see that one of the side lengths is definitely longer than the other ones, and that is right here. And you can always see that it's across from that right angle. It's not connected to it, and it has a special name called the hypotenuse. Hypotenuse. Hypotenuse, kind of a crazy name. Then the other two parts of the right triangle are the ones that sort of make up that right angle, and those are called the legs. So we have one leg and then we have another leg. So those two obviously are shorter. So when you think about the three sides of a right triangle, the two lengths that are shorter, that are smaller in length, are called legs, and the longest side across from the right angle is called the hypotenuse. Okay, so there's a specific formula called the Pythagorean theorem. And I'm just going to write it out here first. It says a squared plus b squared equals c squared. Well, what is it really saying? A and b, in this case, these are the legs. And c is your hypotenuse. So if we just look at the triangle right here on this grid, this would be the hypotenuse. So that length, whatever that length is, would correspond to our c. And then the other two, so here's one of our legs, and here's the other leg. Those would correspond to A and B. And because you're adding them together, it doesn't matter which one's which. So I could, you could call one of them A and one of them B. Someone else could reverse that, and it would give you the same answer because we're just adding, and that's the commutative property that you can add in either order. So I'm just going to go ahead and label this one as A, and this one is B, but just know that that's interchangeable. It does not matter which leg you say is which one. Okay, so let's talk a little bit more about what this formula is actually saying. It's saying if you take this length, whatever this length is, in this case it's 3, but it could be anything, and you square that, and then you take this other length, and this length, in this case it's 4, but whatever it is, and you square that, and you add those two squares together, that answer will equal the square of the hypotenuse. So let's go ahead and plug these numbers in and kind of see what's happening here. All right, so in this particular situation, as we said, A is 3 and B is 4. Okay, now for the length of C, because C is not going along the grid lines, we can't tell by just counting exactly what that length is. So in this situation right now, I'm going to tell you what that length is so that we can see how this formula works. And we'll get into more about how you would actually use the formula to find a missing side, but I wanted to show you the relationship right now. So I'm going to tell you that the length of C is 5. So I just want you to see how these numbers fit together in the formula. So what it's saying is if we take this 3 and square it, which is 9, and the 4 and square it, and we get 16, this should equal this 5 squared, which is 25. And 9 plus 16 is 25. So for every single right triangle in the world, this relationship holds up, where you take one leg and square it, and the other leg and square it, add that together, and it will equal your hypotenuse squared. Just to show you now, well, what would you do to actually find that length, to find that 5? Let's do this formula again. So we're going to do 3 squared plus 4 squared, and we're going to just leave it as c squared, as if we're just going to solve for the c. We want to find out what that missing number is. So we're solving an equation this time instead of just checking it. So we've got 9 plus 16 equals c squared. I would then get 25. And then you can see here it's saying 25 equals some number squared. So think back to algebra. If you want to get c alone, you would take the square root of both sides. You want to get c all by itself, and the opposite of squaring c is to take the square root of c. So the square root of c squared is c, and the square root of 25 is 5. And that's how you would find the missing side if you didn't know what it was. So on the left side, I was showing you how to just plug the numbers in to show that it does actually work. And then here on the right side, we were solving it if we didn't know what it was. Okay, we're going to look at this grid and just kind of talk through this formula a little bit more and see, again, why it's working. And what I want you to do, if you have a color, that would be great, but if you don't, it's fine. We're going to really model the formula on the grid. So to show what a squared looks like, we're going to take, we're going to draw in a square on that side. So we want to draw in a square that's this long. It's 3 lengths long. So we're going to actually draw that square. So you can see now that's the 3 squared, that's the 9. I'm going to do the same thing with the b squared. So over here is our b, and now I'm going to draw in, that's 4, and 4 squared will make a square, a 4 by 4 square. Okay, so finally, the last square is a little harder to draw because it's not going to be on the grid lines. We know now that this length of c is 5, but we're going to draw in a square that would go right along that side. So it's going to sort of be at a diagonal here. It's not going to be perfect. So just try to make it look like it's approximately the same length. So we know that this is 5, and we know that a square has all the sides of the same length. So just try to replicate this length over here. So I'm going to make that a little bit longer. And then when I draw in this square, that should be a square that's 5 by 5. So if you could imagine taking these 9 little squares right here, and then taking these 16 squares, and picking them up and rearranging them inside here, they would all fit. So this is 9, this is 16, it's 25 of these little squares. They should fit if I laid them down inside of here. So what I just showed you with that drawing would work for every single right triangle in the world. No matter what the lengths were of the 2 legs, we could draw a square on those 2 legs, and the area of those squares, the exact space inside of them, would fit in the square that fits on that hypotenuse. It's a pretty cool model to be able to visualize and see, and there's a physical model in my classroom that can show you this. Okay, find your piece of grid paper. It should look something like this. It doesn't have to be this exact same size. And everyone is going to draw a right triangle on their grid paper. Now, before you get drawing, a couple of rules. First of all, you can't draw the same triangle we just did. I don't want you to draw a triangle that has legs that are lengths 3 and 4. You need to use different numbers. Second, I want you to try to draw a different triangle than the people right next to you. So I don't want everyone saying with your neighbors, okay, let's draw one that's 2 and 5, or whatever the numbers you choose. Just try to be different. So it doesn't matter what the lengths are of the 2 legs. You can choose any numbers, but make them whole numbers just to make this easier. Don't try to draw like half of a square here. So I want you to draw 2 legs. So for example, again, don't want you to follow my example here, but let's say I wanted to do the one I just said, 2 and 5. I would draw one length of 2, and then one length of 5, and then I would draw in my triangle. And that's all you have to do. I'll give you a couple seconds to do that. Check with your neighbors, make sure they're making something a little different than you. And then go ahead and label the lengths of your sides. And then you're going to use the Pythagorean theorem to find the length of your hypotenuse. So I'll do mine, but I want you to write down yours. So in my case, I'm going to do 2 squared plus 5 squared. But that's not what you're going to do. You're going to fill in your lengths. So I got that 29 equals c squared. So when I take the square root of c to find my hypotenuse length, 29 is not a perfect square. So I'm just going to write down that c is the square root of 29. So yours might be kind of like that. You might have something where you can't take the square root of it, and that's okay. So I'll give you a few more seconds here to finish that up. All right, what you're going to do next is I want everyone to really, really quickly go around the room and say the length of your hypotenuse. So in a second, you should pause the video and just quickly go around the room and each person tell what you got for the length of your hypotenuse. So pause the video now. Okay, so what did you notice when you did that? When you went around the room and you heard what everybody said, I'm hoping that you've noticed that there were a lot of answers that had a radical. That many of them, if not all, I'm very curious how this went, but many of them ended up where the answer was a radical. And that is not unusual. Most right triangles, when you have two lengths for the legs, most right triangles, the hypotenuse is going to be a radical, and that's normal and usual, and that's going to happen. However, as you saw earlier, when we had the triangle where the lengths were 3 and 4, and the hypotenuse ended up being 5, that does happen sometimes, and that's really a special case, and that is something called a Pythagorean triple. So a Pythagorean triple is when you have 3 lengths of a right triangle that are all whole numbers. And again, that's pretty unique. So we saw that the one we saw earlier today is one that we know. It's called the 3, 4, 5 right triangle. You'll notice that you're going to see that triangle a lot. It's pretty kind of a popular right triangle because it is nice whole numbers where there's not many right triangles that have low numbers that are like that. Now you can take this 3, 4, 5 right triangle and you could double those side lengths or triple those side lengths, and you would get other right triangles that also work, and they're in that same family of the 3, 4, 5 right triangle. So for example, I could double these numbers and get 6, 8, and 10, and that would be another Pythagorean triple. If you plug that into Pythagorean theorem, it would work. 6 squared is 36, 8 squared is 64. If you add 36 and 64, you would get 100, which is the 10 squared. If you had tripled those original numbers, 3 squared being 9, 3 tripled is 9, 4 tripled is 12, and 5 tripled is 15, that's another Pythagorean triple. Again, they're all in this same family, so if you tried those out, those would also work. There are a few other Pythagorean triples that I'm going to show you today, and it's kind of helpful to have these in your head that you can memorize them, because it just helps you to see, if you see them, you're going to know, oh yeah, that is definitely a right triangle. So the next one I want you to know about is 5, 12, and 13. If you want to just check this real quick in your head, 5 squared would be 25, 12 squared is 144, and then I'm just going to jot this down so you can see it. 25 plus 144, if I add that together, I'm going to get 169, which is what 13 squared is. So that does work. Just wanted to show you that, but I'm going to erase this because I want to write down the doubles and the triples of that. So for example, if I took 5, 12, and 13 and I doubled those numbers, I would get 10, 24, and 26. So that's another Pythagorean triple within that same family. And we could triple that and we would get 15, 36, and 39. I don't think you need to memorize all these, but if you notice, well, if I just divide all those by 3, I'm going to get 5, 12, 13. And you could keep going. There's no limit to how many times you could do that. All right, we're going to do one more Pythagorean triple here, and the last one I'm going to show you is 7, 24, 25. Okay, so again, just to show you that this does work, 7 squared is 49, 24 squared is 576, and 25 squared is 625. If you just look at these two numbers, if you add that together, you will get 625, just to show you that it does work. And then just to write down, again, if you had doubled these numbers and got 14, 48, and 50. That would be another version of that. I'm not even going to do the triple one of this one. But these are Pythagorean triples where the lengths of all three sides, the two legs and the hypotenuse, are all whole numbers. Again, very unique. It doesn't happen very often. You're most of the time going to have radicals as one or more of the side lengths, which is, as we're going to see in here in a little bit. So Pythagorean triples, something good for you to know about. All right, so the kinds of questions you're going to get to see a lot with Pythagorean theorem is sometimes I'm going to give you three side lengths and I'm just going to say, do these side lengths make up a right triangle? We want to know, do they actually make a right triangle? Is one, is one of the angles in that triangle a right angle? And the way you can figure that out is you would plug the numbers into the Pythagorean theorem and see, do they work? Do they actually make the a squared plus b squared equal c squared? So you do it like a check where you plug the three numbers into the check. So let's go ahead and do that for this first one. We've got 20, 28, and 19. So I'm going to write down my formula. And you might be wondering, or hopefully you're wondering, well, how do you know what to put in for which thing? How do you know what to put in for the legs for A and B and what to put in for C? And hopefully you can remember from the very first thing we talked about today is that the hypotenuse has to be what? The longest side. So therefore, if you look at your numbers, then in this situation, 28 needs to be my hypotenuse. So let's plug these in. 28 for the hypotenuse, and 20 and 19, it does not matter which one goes in for A and which one goes in for B. Okay, so 20 squared, that's 400. 19 squared, do you remember this from learning these last year? That's 361. And 28 squared wasn't one you had to memorize, but that is 784. So again, we're doing a check. We're trying to see, does this work? If I add the numbers on the left, 400 plus 361, I get 761. That does not equal 784, which means, therefore, no, this is not a right triangle. They did not work in the Pythagorean theorem. All right, let's try the second one. So looking at these numbers, the largest one, the 25, is going to be our hypotenuse. So we plug this in. 8 squared. And then the other leg would be 24 equals 25 squared. All right, so 8 squared, that's 64. And 24 squared is 576. 25 squared is 625. And when we add these together, let's see, 4 and 6, that's 10. Should be 640. Okay, so once again, this one did not check out. This is not a right triangle. It did not fit into the Pythagorean theorem, so those three lengths cannot make a right triangle. Okay, for our third one, we have 65, 60, and 25. So obviously the longest side is 65. So we'll plug in our other legs, 60 and 25. Well, 6 squared is 36, so that makes 60 squared 3,600. 25 squared is 625. And 65 squared, not one that I'm sure you know, but it is 4,225. All right, so when I add 3,600 plus 625, I do get 4,225. So this one does work. This does make a right triangle. It does fit into the Pythagorean theorem, so yes, this one works. Okay, when we get to our next row, you'll notice that there's some radicals here. So sometimes the side lengths are radicals. So you have to first decide, well, just like last time, which one is our hypotenuse? Is radical 29 definitely bigger because it's 29? Not necessarily. So what we have to do before we can decide which one is our hypotenuse is we either need to think of all three numbers as numbers outside the radical, or we need to think of all three numbers as numbers in the radical. They're all going to work. Both ways are going to work. It's just a matter of being consistent. So for example, I could think of these as numbers outside the radical, meaning what is the square root of 29? What number is that really? Even if you don't have a calculator, you could just think about what you know about the number 29 and what perfect squares are around it. Since 25 is a perfect square, and that's lower than that, and the square root of 25 would be 5, right? So the square root of 29 must be something bigger than 5. And 36 is another perfect square, which is higher than that, and the square root of 36 is 6. So you can see then that the square root of 29 must be between 5 and 6. It's somewhere between 5 and 6. So I'm just going to write down here that it's 5 point something. We don't really care what it is, but it's 5 point something. So now I'm comparing 5 point something, and 2. So now I can see, well, the square root of 29, the 5 point something, is obviously the biggest number. If that feels too hard to do in your head, the other way you can do this is you can think of it from the other perspective of putting them all back in the radical. So if I were to square 5, I would get 25. So I could think of it as the square root of 25. And then I have the square root of 29, and I could square 2, and I really have the square root of 4. And once you have them all in radicals, you would still just look at which number is the biggest number now. You could compare them just inside the radicals. And so again, radical 29 is still my biggest number. So with that in mind, now that I know which one's the hypotenuse, I'm going to plug this in with my radical 29 going in for C. Notice how I'm writing that down. I'm squaring radical 29. So I'm putting it in parentheses. And then I'm going to take the other two, 5 and 2, and put them over here. So we have 5 squared plus 2 squared equals the square root of 29 squared. Well, the left side, that's nice and easy, 25 plus 4. But on the right side, do you remember when you square a radical, the square and the radical just cancel out. So therefore, the square root of 29 squared is just 29. Looks complicated, but it ends up being nice and easy. So now we just add this together, and we get that 29 does equal 29. And so yeah, this one worked. This was a right triangle, yes. All right, the next one, they're all radicals. We don't really have to do any changing because they're all 3 radicals. So when I look at these 3 numbers, radical 15, radical 27, radical 12, I can be assured that radical 27 is the biggest one. That's definitely going to be my biggest one. I can put it in for C in my formula. So I've got the square root of 15 squared plus the square root of 12 squared. And we want to see if that's going to equal the square root of 27 squared. Again, those square roots in the squares just cancel out. So this leaves me with 15 plus 12 equals 27. And it works. So yes, this one is another one that works in the Pythagorean theorem. So it's a right triangle. It is. Are you ready to try one by yourself? I think you are. Why don't you go ahead and fill in this last one on your own. So go ahead and pause the video, try it by yourself, and then check back in and you can see how you did. Pause the video. Okay, how did you do? First of all, I hope that you realize that the radical 48 is the hypotenuse. That's the biggest one. So I hope you put everything in the right way. And then once you squared all this, you got 20, 25, and 48. And 45 does not equal 48, so these 3 did not make a right triangle because they did not fit into the Pythagorean theorem. Okay, so the other way that you'll often use the Pythagorean theorem is to find a missing side. This is probably what you'll use more often, is if you know 2 of the sides of the right triangle, you can find the 3rd side by using the Pythagorean theorem. Now, in this situation, we have a picture and we can tell that the missing side in this first one is the hypotenuse, right? This is right on the longest side. It's across the right angle, so we know that we're looking for the hypotenuse. So when I start with my formula, I know that the one I'm looking for is x, is going to go here in for C. And then the other 2, because they're next to the right angle, they sort of make up that right angle, they're going to be my legs. So we have 2 of the lengths of our triangle are 7 and 6, and we're going to find that 3rd length, the hypotenuse. So 7 squared is 49, 6 squared is 36. This gives me 85. And we want to find the square root of both sides. Now, if we could simplify this, we would. If there was any perfect squares that goes into 85, we would simplify that, but there's not. Obviously 5 does go in, but it goes in 17 times. It's another prime number, so we can't simplify that. So the length of my hypotenuse here is just radical 85. Now, there are some situations where you would want to make that into a decimal, but that we don't need to do that very often. That's more of like a real life situation if you wanted to know, like if you're measuring something and you need an actual number. But in this classroom, most often you are going to just leave it as a radical unless I tell you otherwise. We like to leave things in simplified form, which is what this is. We don't want to have to round it to a decimal. Okay, for the second one, this time they gave us the hypotenuse and we are looking for one of the legs. So we have x squared plus 14 squared equals 20 squared. So we haven't seen this type yet. Okay, so x squared and then 14 squared is 196. Knowing those squares from last year will definitely come in handy here. And then 20 squared is 400. So we're just solving an equation. We just want to find, we want to get x alone. So thinking back to what you would have done in algebra, we're going to subtract this 196 from both sides. We get x squared equals 204. Take the square root of both sides, so we get the square root of 204. And we can simplify this a little bit because 4 goes into this. 4 goes into this 51 times. So we would get radical 4 and radical 51. Oops, I have 2 equal signs there. And that gives me 2 times the square root of 51. And that's as far as we can go. I should also have pointed out earlier that anytime you take the square root of both sides, or take the square root of something in algebra, like for example in this first one, if this was just an algebra problem, the answer here would have been plus or minus the square root of 85, if that was just an algebra question. However, in geometry, because we're finding the length of that side, that length can't be negative. It can't be a negative length. That's just impossible. And so we don't need that here. It's not that we're never going to have that in our geometry class. Sometimes we will, but if it's representing a length, then it's just impossible to have the negative. So I don't want you to forget about the algebra rule that taking the square root of both sides would end up giving you a positive and a negative version, but we just don't need that in this situation. So it's good to think about, well, there are 2 answers to that equation, but only one answer in this geometric situation because we're looking at the length of a side of a triangle. All right, let's get this third one done. We've got that the hypotenuse is 12, and we're going to be finding one of the legs. So we have 9 squared plus x squared equals 12 squared. 9 squared is 81. 12 squared is 144. Again, we want to get that x alone, so we're going to subtract 81 from both sides. So we have that x squared is going to equal, oops, I have an extra 1 in there. Just 81, not 181. So we have 63, and then we want to take the square root of both sides. So we have the square root of 63, and think about what perfect square can go into 63, and that's 9. So we have radical 9 and radical 7. And then finally, 3 radical 7 will be our answer. Okay, for these last 3, you'll notice that, again, some of the side lengths happen to be radicals. So let's go ahead and look at this one. We've got 5 radical 13 is my hypotenuse. That is across from my right angle, right? So that's going to be the hypotenuse. So when I plug this in, 5 radical 7 will be one of my legs. 5 radical 7 will be one leg. X will be the other leg. And then 5 radical 13, that's going to be my hypotenuse. Okay, this one's a little more complicated because we're squaring not just a radical, but we're squaring the number in the front as well. So when I square 5 radical 7, well, this radical 7, the radical goes away. So radical 7 squared is just 7. But I also have to square the 5. So it's really 25 times 7. And remember, there's a multiplication between the 5 and the radical 7. So there has to be a multiplication here. So 5 squared is 25. Radical 7 squared is the 7. That's where that's coming from. And then the same thing here. When we square the 5, we get 25. And when I square radical 13, I just get 13. So we've got to finish this multiplication before we can solve for our x. So 25 times 7, that's 175. And 25 times 13, let's see, 4 quarters and $1. So 4 25s, we got 12. That's going to be 325. All right, and then we're going to subtract 175 from both sides. And we have x squared equals 150. Take the square root of both sides, and x is the square root of 150. And what perfect square can go into 150? It's 25. So that gives me radical 25 times radical 6. And my final answer is 5 radical 6. All right. I think you should try the second one by yourself. So in a second, pause the video, work through the second one, and then check back in after that one, and we'll see how you did. Pause the video now. All right, welcome back. Hopefully you got for the answer for the hypotenuse, radical 86, that cannot be simplified. There's no perfect squares that can go into that number. And if you have any questions, you can pause and look through my steps here. All right, for the third one, again, I want you to pause the video and do that third one by yourself, and then come back and check in and see how you did. All right, welcome back. Let's see how you did. The answer to this missing leg is 4 radical 6. And if you didn't get that, just sort of check the step above it. Maybe you got radical 96 and didn't simplify it, or maybe you first took a 4 out of 96, which was 4 times 24, and then didn't simplify it further after that. So hopefully you can get your way down to 4 radical 6 for the missing leg for this side. And that's it for the Pythagorean theorem notes.